6.141. That is the orbital eccentricity of an object detected on July 1, 2025, by a survey telescope in the Chilean desert. To put that number in context, anything above 1 means an object is not gravitationally bound to the Sun. Anything above 1 means it came from somewhere else. It arrived from outside our solar system, passed between the orbits of Earth and Mars, and kept going. It will never return. It is only the third time in recorded history that something from another star system has crossed through our neighborhood. The first was a dry, cigar-shaped rock that accelerated for no known reason. The second was a snowball rich in carbon monoxide that looked almost normal. The third, the one carrying an eccentricity so high rewrites the speed record for interstellar visitors, was neither. It was releasing water. 70 Olympic swimming pools worth of water vapor per day. At a distance from the Sun where most comets in our own solar system do not even wake up. The telescope that found it is called ATLAS, the Asteroid Terrestrial Impact Last Alert System. It was not built to discover interstellar comets. It was built to find objects that might hit Earth, asteroids on collision trajectories, the kind of thing you want to know about before it arrives. The system operates from a facility at 2,300 meters altitude in Rio Hurtado, Chile, part of a network funded by NASA's Planetary Defense Coordination Office. On that night in July, one of its automated cameras captured a faint dot at magnitude 19.6 near the edge of what the system was designed to detect, dim, easy to overlook. The kind of signal most survey pipelines would have flagged, logged, and moved past without a second thought, but the dot moved. And the direction it moved did not match any known orbit in the solar system's catalogue. Follow-up observations started within hours. Professional astronomers first, then amateurs with backyard telescopes contributing astrometric data, then more professionals joining from observatories across 3 continents. Within 48 hours, the orbital calculation was complete, and one number settled every question: eccentricity, 6.141. For comparison, one Oumuamua, the first interstellar object ever detected back in 2017, had an eccentricity of 1.2. 2I Borisov, the second, found in 2019, came in at 3.4. 3I Atlas was nearly double Borisov and 5 times Oumuamua. It was traveling faster relative to the Sun than anything from outside our solar system that humanity had ever tracked. On August 20th, 2025, the Hubble Space Telescope pointed at the new object and estimated a nucleus diameter somewhere between 440 meters and 5.6 kilometers. That range is enormous. It tells you how difficult it is to measure an object that is small, fast, and shrouded in its own gas. But even the lower estimate made 3I Atlas substantially larger than Oumuamua, and potentially larger than Borisov. It was getting brighter as it approached the Sun, its coma expanding and reddening, the first chemical signatures of a distant star system beginning to leak into our instruments. Think about the improbability of that detection for a moment. A planetary defense telescope in Chile, scanning for asteroids, catches a faint smudge of light moving in the wrong direction. Within days, it is confirmed as only the third object from outside our solar system that humanity has ever recorded. And unlike the first 2, this one arrived with chemistry we could read: water, organic compounds, dust that scatters light in ways we have never seen. The designation says it plainly: 3I, the third interstellar object in the history of human observation. In 8 years, we went from 0 to 3. And this time, unlike the first, the visitor was willing to talk. To understand why 3I Atlas matters, you need to understand what came before it, and why the first visitors left us arguing more than they left us informed. 1I Oumuamua arrived in October 2017. It was the first confirmed interstellar object in the history of astronomy. And it was, from the very first observation, a problem. It had no coma, no cloud of gas or dust around it, which is what comets do when they approach the Sun and their ice begins to sublimate. It had no tail. It appeared to be a dry, flat, elongated body, somewhere between 100 and 1,000 meters long, tumbling through space with a rotation period of roughly 7.3 hours that suggested it was not a sphere at all, but something closer to a disk or a pancake. No known natural formation process produces that shape easily. That was strange enough. But what made Oumuamua genuinely unsettling was the acceleration. As it moved away from the Sun, it sped up, slightly, but measurably, in a way that gravitational physics alone could not explain. Something was pushing it. Solar radiation pressure was proposed as a mechanism, but that would require Oumuamua to be implausibly thin. Outgassing from hydrogen ice, a type of ice so volatile it would sublimate invisibly, leaving no detectable trail, was proposed by Seligman and Laughlin. Avi Loeb at Harvard proposed, with full seriousness and a peer-reviewed paper, that it was an artificial object, a light sail from another civilization. None of these explanations have been confirmed. None have been decisively ruled out. Oumuamua left our solar system without answering the most basic question about itself. What it was made of. To Borisov arrived 2 years later, in August 2019. It was discovered by an amateur astronomer named Gennady Borisov, working with a 0.65 meter telescope he had built himself in Crimea. And it was the opposite experience. Borisov looked almost exactly like a solar system comet. It had a coma, a tail, a clean hyperbolic trajectory. Spectroscopic analysis showed it was rich in carbon monoxide, unusually rich, with CO levels about 9 times higher than what you find in typical comets near the Sun. But structurally, behaviorally, Borisov acted the way textbooks say comets should act. It was reassuring. It suggested that other star systems produce objects that look and behave like the ones we know. Then came 3IATLAS, and it refused to fit into either category. It had a coma, so it was active, unlike Oumuamua. But its activity was dominated by water vapor, not carbon monoxide, so it was compositionally distinct from Borisov. Its surface was coated in tholins, a class of reddish organic compounds that form when simple molecules, like methane and nitrogen, are irradiated by cosmic rays over extremely long timescales. Its color was redder than most solar system comets, and its polarimetric properties, the precise way its dust particles scattered sunlight, had never been recorded on any comet or asteroid in our solar system, or any interstellar one. 3 visitors from 3 different star systems. A dry rock that accelerated for no known reason. A carbon monoxide snowball that behaved by the book. A water-bearing, tholin-coated anomaly with dust that breaks every existing model. 3 objects, and not one of them resembles the others. The sample size is absurdly small. 3 is barely a dataset. But the implication is already uncomfortable. If every interstellar object we catch is a complete surprise, chemically and physically distinct from the last one, what does that tell you about the diversity of planetary systems across the galaxy? It suggests that the processes that form and eject material vary enormously from star to star. And it means we cannot predict what the 4th visitor will look like. Let me be specific about what made 3I Atlas unlike anything we had measured before. Because the details are where it gets genuinely strange. Start with the water. When 3IATLAS reached perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of 1.36 astronomical units, roughly between the orbits of Earth and Mars, it was releasing approximately 70 Olympic swimming pools worth of water vapor every single day. That is an extraordinary volume. Most solar system comets at that distance show modest activity, a gentle sublimation, a thin haze. 3I was outgassing with a violence that surprised the teams tracking it. The European Space Agency described the output in plain terms, extraordinary, and the pattern of that outgassing was revealing. Most of the vapor was being flung sunward, which suggested that the outgassing was concentrated on the sunward face of the nucleus, a pattern consistent with a surface crust fracturing under thermal stress, exposing fresh ice beneath. The water mattered because it told a story about the comet origin. This was not the exotic carbon monoxide ice of Borisov. This was water ice, the kind that forms in the habitable zones of star systems, or in the outer reaches of protoplanetary disks where temperatures allow H2O to freeze. Whatever star 3I Atlas was born around, that star planetary system had the conditions to produce water ice in abundance, and that ice survived a journey of 800 million years through the vacuum of interstellar space, insulated beneath a crust of irradiated organics that acted like a blanket. Then there were the tholins. Tholins are not a single molecule. They are a class of complex organic polymers that form when simple carbon and nitrogen compounds are exposed to ultraviolet radiation and charged particle bombardment over millions or billions of years. The name was coined by Carl Sagan in 1979. You can see them on Pluto reddish plains, in Titan orange atmospheric haze, on the darkish trans-Neptunian objects at the edge of our solar system. The tholins on 3IATLAS were consistent with this chemical family, but subtly different. The spectral slope in the 5,000 to 9,000 angstrom range was steeper, redder, than most solar system comets, though similar to some Centaurs and D-type asteroids. Every angstrom of that excess red is a chemical record, a clock written in molecular damage. The longer the exposure to interstellar radiation, the deeper the red, the spin told its own story. 3I Atlas rotated with a period of 16.16 hours, plus or minus 1/100th of an hour. That is remarkably precise for an object we had only weeks to observe. The light curve showed an amplitude of about 0.3 magnitudes, meaning the nucleus was not spherical. It was elongated enough that its brightness varied noticeably as it tumbled. And then there was the polarization. When sunlight scatters off dust grains in a comet coma, the scattered light becomes partially polarized. The degree and direction of that polarization, how it changes with the angle between the sun, the comet, and the observer, is a fingerprint of the dust. Grain size, shape, composition, porosity, all encoded in the polarimetric curve. 3I Atlas showed an extremely negative polarization at small phase angles. The combination of low inversion angle and extreme negative polarization had never been seen on any comet, any asteroid, any object in the entire solar system. It was, in the strictest sense of the word, unprecedented. The first object known with that specific polarimetric behavior. What kind of dust produces that signature? What is different about the grains, their shape, their structure, the way they were forged in another star radiation field? Those questions remain open. And they may stay open until we catch another visitor carrying similar dust. On October 14th, 2024, a Falcon Heavy rocket launched from Kennedy Space Center, carrying the largest spacecraft NASA had ever sent to the outer solar system, Europa Clipper. Nearly 6 tons of instruments, solar panels, radiation shielding, and propellant, designed and built for a single purpose: travel to Jupiter moon Europa, perform 49 close flybys over 4 years, and determine whether the ocean beneath 20 kilometers of ice has the conditions to support life. The journey to Jupiter would take 6 years. The spacecraft would use gravity assists from Mars and Earth to build enough velocity to reach the Jovian system by 2030. Nobody on the mission team designed Europa Clipper to look at comets. It carries 9 scientific instruments: ice-penetrating radar, a magnetometer, a thermal emission imaging system, a mass spectrometer, and more, all optimized for one target. Nobody planned for an interstellar detour. Nobody imagined there would be one. 9 months into its cruise, in the summer of 2025, 3I Atlas reached perihelion. Europa Clipper was deep in the inner solar system, more than 160 million miles from Earth, quietly running instrument calibrations and coasting toward its first gravity assist at Mars. The spacecraft had already proven its hardware. During the Mars flyby in March 2025, the team tested the ice-penetrating radar, bouncing signals off the Martian surface to validate that the instrument worked as designed. Everything was on schedule. Everything was routine. And then the comet geometry changed everything. By November 2025, 3I Atlas had moved to a position that was geometrically hostile to Earth-based observation. The Sun was directly in the way. Ground-based telescopes could not see the comet through solar glare. Mars-based instruments and observations coordinated with other assets had already lost their optimal viewing angle. For several critical weeks, the comet was undergoing some of its most intense post-perihelion outgassing activity, shedding water vapor, dust, and the chemical record of another star system, and nobody on Earth or Mars could watch it happen. But Europa Clipper could. The team at the Southwest Research Institute, led by principal investigator Kurt Rutherford, realized that their ultraviolet spectrograph, the instrument they called Europa UVS, had the geometry, the sensitivity, and the spectral range to observe 3I Atlas during the blackout window. The spacecraft position in the inner solar system illuminated a clear line of sight that no other observatory in existence could match. Rutherford described the opportunity in plain terms. It was completely unexpected. Europa UVS was built to measure the composition of Europa tenuous atmosphere and to detect plumes of water vapor erupting from cracks in the moon icy crust. It is particularly adept at reading the fundamental atomic and molecular transitions that occur when water molecules are broken apart by ultraviolet light, hydrogen atoms flying one way, oxygen atoms the other. It was designed to detect water being ejected from an icy body into space, which is exactly what a comet does when it passes near the Sun. The team pivoted. They wrote new observation sequences, uploaded them to the spacecraft across 160 million miles of space, and pointed Europa ultraviolet spectrograph at 3IATLAS. And for several weeks in November and December 2025, a 6,000 kilogram spacecraft built to study the habitability of an icy moon orbiting Jupiter turned its eyes toward a visitor from another star system entirely. It was the kind of opportunistic science that space missions rarely get to do. An instrument designed for one ocean, reading the chemistry of another world debris, the UVS. Data confirmed what ground-based observations had suggested, and then extended the record into a period that would otherwise be permanently blank. Europa Clipper detected hydrogen and oxygen in the coma of 3I Atlas. These are the dissociation products of water when solar ultraviolet light strikes water molecules and breaks them apart. You get hydrogen atoms and oxygen atoms expanding outward from the nucleus in all directions. The detection confirmed that 3I was actively outgassing water at a significant rate during the weeks immediately following perihelion, the period of peak thermal stress on the nucleus. But the UVS also registered dust-related spectral signatures, evidence that the outgassing was not gentle. Gas and dust were being ejected together, the surface crust fracturing and shedding material as internal ice sublimated and pressurized the porous interior beneath. This was data that no other instrument in the solar system could have collected during that window. Without Europa Clipper, there would be a gap in the observational timeline, a missing chapter during the comet's most active and scientifically valuable phase. The spacecraft bridged the interval between Mars-based observations in late September and Earth-based recovery weeks later. A single ultraviolet spectrograph, never designed for this target, never intended for this purpose, filled a hole that the entire ground-based and space-based observatory network could not. But the most profound finding about 3I Atlas did not come from the ultraviolet data. It came from the trajectory. By modeling the comet's path backward, not just through our solar system, but through the Milky Way itself, astronomers traced its galactic origin. And the answer was not what anyone would have guessed. 3I Atlas did not come from the thin disk, where our Sun lives, where most relatively young stars orbit in a flat, orderly plane close to the galactic midplane. It came from the thick disk. The thick disk is an older, puffier layer of stars that extends above and below the galactic plane. Its stars formed 7 to 10 billion years ago, during the chaotic early assembly of the Milky Way, long before the Sun ignited, long before the Earth coalesced from the solar nebula. Some of those ancient stars built planetary systems, and some of those planetary systems, through gravitational encounters with giant planets, passing stars, or the slow tidal stirring of the galaxy itself, ejected material into interstellar space. 3I Atlas was one of those ejections. The estimated travel time through the void, approximately 800 million years. Think about what that means. When this comet left its home system, the most complex life on Earth was single-celled. Multicellular organisms had barely begun to appear in the fossil record. The comet drifted in total darkness for longer than animals have existed on this planet. Its water ice locked beneath a crust of tholins that thickened decade by decade under the relentless bombardment of cosmic radiation. The tholins on its surface were forged by the radiation environment of a star that may no longer exist in the same form. The water ice in its interior crystallized in a protoplanetary disk that orbited a sun born before Earth's raw materials had even begun to gather. Every molecule on 3I Atlas carries a timestamp from the early galaxy. It is not just a visitor. It is a sample, a piece of physical evidence from the first generation of planetary systems, delivered to our doorstep by nothing more than gravity and 800 million years of patience. Here is the question that 3I Atlas forces you to sit with. We have detected exactly 3 interstellar objects in 8 years. The first, Oumuamua, was found by accident. A survey telescope caught it 19 days after it had already passed its closest point to the Sun, on its way out. The second, Borisov, was spotted by an amateur astronomer in Crimea using a 0.65-meter telescope he had built himself. The third, 3I Atlas, was flagged by a planetary defense system in Chile, a telescope designed to find things that might hit us, not things passing through from another star. 3 objects. 3 completely different discovery methods. 3 completely different compositions. The only thing they share is that we barely caught them at all. Statistical models built on these detections, admittedly fragile models, given the sample size of 3, suggest that interstellar objects pass through the inner solar system not occasionally, but regularly. Some estimates put the number at several detectable objects per year. If our telescopes happen to be looking at the right patch of sky at the right moment with the right sensitivity. The overwhelming majority pass through unseen. And below the detection threshold, smaller, fainter, faster, the numbers could be orders of magnitude larger. The space between stars is not empty. It is seeded with the debris of planetary formation from billions of star systems across the Milky Way. We have been swimming in it for 4.5 billion years. We are only now building the instruments sensitive enough to notice. The Vera C. Rubin Observatory in Chile is expected to begin full science operations with its legacy survey of space and time in 2026. It will image the entire visible sky every few nights with a sensitivity and cadence that no previous survey has approached. Current projections suggest Rubin could detect roughly 1 interstellar object per year, perhaps more. If those projections hold, 3 IATLAS will not remain a curiosity for long. It will be the first entry in a catalogue, and a catalogue changes everything about the science. With 1 interstellar object, you have an anecdote. With 3, you have a pattern that might be noise. With dozens, with a genuine statistical sample, you have a new discipline entirely. Interstellar material science, the ability to study the chemistry of other star systems using physical samples delivered to our solar system by the galaxy itself, readable with instruments we already possess or are building right now. Europa Clipper, meanwhile, continues its long cruise toward Jupiter. Its Earth gravity assist is scheduled for December 2026, arrival at Europa in 2030. 49 flybys of an ice-covered moon whose saltwater ocean holds roughly twice the volume of all the water on Earth. The spacecraft that was designed to study one moon has already contributed to the study of a visitor from another star. The UVS instrument that will one day search for plumes of water erupting through cracks in Europa's ice has already measured water erupting from the surface of a comet that was born before this planet existed. And 3 IATLAS is still out there, moving away from the Sun at a velocity the solar system cannot overcome, carrying its tholins, its unprecedented dust, its chemical biography written over 800 million years, back into the dark between the stars. In a few decades, it will be beyond the reach of any instrument humanity possesses. It will rejoin the interstellar medium and continue its drift, the same drift it has been on since before complex life appeared on Earth. The galaxy sends us samples. We had a few months to read this one. The question is not whether the next one is coming. It is whether we will be ready when it arrives. Thanks for watching, and I'll see you in the next one.